Hi all, welcome to part 15 of the video lecture on counters. So this is a continuation of the part 14, right? So follow that, then you will understand this. So in part 14 we discussed something called ring counter, and now we are just going to see a slight variation of the ring counter here. So that is something called as a Johnson counter, the person who introduced this concept for the first time. So it's otherwise called a switch-tail ring counter also, right? And we will see it's very simple. The ring counter configuration, hope you remember, like the set of D flip-flop we are connecting like in a shift register fashion, like the output of the first one, say A, B, C, D, E, we are denoting the output like that, and this is connected as input to the second one output, like that you are connecting, right? So you don't have to put the arrow anyways. And hope you remember in ring counter what we done is the output in a ring manner, the output of this last one we connected to the first one, right? So that is our ring counter. Now we are just making a small variation, that is instead of connecting the last output as to the first one, its complement we are taking, and that we are, and for in every flip flop we will get this output and its complement, so but they are complementary, right? So you will always get it's easy for you to take the complement of it, or you take and use a NOT gate and you connect back like that. The only thing is what is the actual output of the last flip flop, take its complement. So that is by default in any flip flop available, and that you should connect to the first one. Now same way you feed that 1 0 0 0 into the flip flop, like what we seen in our ring counter. So if you are observing this ABCD, what you are doing is 1 0 0 0 you are feeding into the circuit somehow. Okay, so so maybe in a parallel manner, or in a serial manner, or after another, maybe after 4 clock cycles, something like this is inserted into the flip flop. So that input is not shown here, we are just focusing on the output only, and this output you are observing like this: what is your A, what is your B, and what is your C. And these things you are actually connecting to 4 different devices for enabling them, maybe as a timing signal, but not this one. With this you will do some slide at this one, and that output you will connect, and that we will see. So what we are going to do is, so if this is a case, can you tell me the output? And remember the complement of the last one is connected as a input, okay, to the first flip flop, so that after a single next first clock cycle, this will shift, like this one will come here, this 0 will come here, this 0 will come here, and the last 0 in ring counter moved here, right? But here its complement is moved here, so instead of that 0, the last bit flip flop is giving a 0, its complement 1 will come here. And then in the next clock cycle, this 1 will come here, this 1 will come here, and this 0 will come here, and this 0 its complement 1 will come here. Now in the next clock cycle, what it will do, this these 3 ones will shift like this, and 0 its complement is 1, like that. And in the next clock cycle, what will happen, these 3 ones will shift, and the last one its complement is something like a 0. So like that it will keep on counting. And can you tell me how many count? Okay, let's finish it will finish soon. And now in the next clock cycle, what will happen, this 0 1 1, like that shifting will happen, and its complement 0 will come here. In the next clock cycle, it's like zeros, this 0 will come here, this 0 will come here, this one, and this complement will come back here. And in the next clock cycle, it will go to something called these 3 zeros are shifted like this, and this one its complement come over here. Actually there is some problem, let me check it. It's correct only. In the textbook they started with the 0 0 0, then some 1 needs to be inserted anyway, so this way also will work, no problem. Now in the next clock cycle, this 0 complement 1 will come, something like this, and this is nothing but this starting one, then it will repeat from here. Okay, so this whole thing is to be repeated, something like this. Okay, in the next clock cycle, this will repeat the first sequence. Okay, let me write it like this, and what this 0 complement and other zeros are like this. So this many distinct states are here, 8 different distinct states you will get using after 8 clock cycles, and the 9th one is actually the first one repeating. So I can say that there are 8 states for it. okay, and you implement it using a 4-bit shift register using 4D flip-flops. You can now generate 8 different unique output combinations. So this is listed here also. Here they started with the 0000, then 1000. I just started with this count, so both are fine, okay, and then finally after 0001, next we are going to 40, and then this one, like that. So this many different unique states are being coming as the output of the Johnson counter. So still that is clear. The only thing, only difference from the ring counter we explained in the previous slide is the last flip-flops complement output we connected to the first one's input, so that it's going through this kind of a counting sequence at the every clock edge, like that, okay. Now what we are doing is we are supposed to generate the timing signal, right? So we have to generate timing signal for some n devices, so that we are having on the background one way of achieving it is that counter and decoder combination we discussed in the previous video. Another way of generating the counter signal in a systematic way is that ring counter. Now this is the third way of doing the same, but it is having some benefit. We can achieve more timings, and we can generate some 8 different timing signal using 4 flip-flop, but in the ring counter 8 different timing signal we generate using 8 flip-flops. Hope you remember. Okay, so now how the final timing signals is generated, and that is using some additional level of AND gate. And that AND gate also, it's not like the decoder. Hope you remember, for a 4x16 decoder you need 16 AND gates, so 4 input, 4 input AND gates you want. But here the AND gates are just a 2 input AND gate only. And how many flip-flops are there? There are 4 flip-flops only needed, but it is generating 8 different sequence, counting sequence, unique sequence, and those 8 different sequence you are fed into 8 different AND gates, okay. And the AND gates inputs are like for the first AND gate, so it's like this, these devices will generate the output like this A, B, C, D, E you will take, right? Then how many AND gates you are having? You are having AND gates like, so let me draw the AND gate in a okay, so what I can do is I can, so for easy understanding, let me remove the output from this point. So somehow you have to take the output. Okay. Now the outputs are coming out like this. Okay, I'm just drawing like this. Don't worry about that crossing and all. So it's not crossing, okay. Or in a exam, if you want to show, you can. It's better to do this something like this, okay. I don't want it now, so that's why. Oh yeah, and there is one more output, okay. So and these 4 outputs are going through these 8 different states. Now I will use something like this is my first AND gate, second AND gate, this AND gate, third AND gate, fourth AND gate, fifth AND gate, sixth one, seventh one, and eighth one. Why I am using 8 different AND gate? Because 8 different counting sequences are there. Now each one is now going to, the output of each one is going to activate a particular device. So this is going to activate device 1, device 2, device 3, right? So that I can activate 8 different devices, or I can generate timing signal for 8 different devices that made a particular digital system, right? Using a logic like this, okay. And how to give the input to the AND gate. So that's important. So the thing is that at any time only one of the combination is being generated, and accordingly accordingly when 000 is generated, 100, so one of the AND gates should be enabled. So that's very important. Just like a decoder, n inputs will be coming and 2 power and output combination will be, but at any time using that n input, decoder will activate only one of the output, no, all others will be 0. So just like that here also I have 8 different AND gates, so I have to give the input to the AND gate in such a way that only one AND gate is activated at any time, others are deactivated. So that I have to ensure. So let me just tell you, if for all 0, what they are doing is they are taking the first one and the last one, A and E. Their complement is fed as input to the AND gate. Now can you tell me A dash, E dash? A dash and E dash is getting 1 for this particular combination, right? So 0 0 0 0, whenever the output of the 4 D flip-flops that's connected in the twisted ring counter manner is giving an output like a 4 0 0 0 0, you can see that A dash E dash is giving a 1. Now at this point, I'm for this particular input, can you tell me what is A B dash? A B dash, A is 0, so this is 0. What is B C dash? B C dash, B is 0, so this is 0. C E dash, C is 0, this is 0. Anyway, this is 0. A dash B, one of the input is in uncomplemented form, so all of them will be 0. So what I was trying to say is, when the input is something like A equal to B equal to C equal to E equal to 0, I mean all 0, only this A dash E dash, the first AND gate alone is giving a 1, all others are giving a value of 0. Is this clear? So this is just working like our decoder only. Similarly for the second one, I mean for when the output is something like, so A, you just take A dash, okay, so you can take this A dash, okay, I may be using, anyway for having this kind of a diagram, this line is also needed, yeah, or let it be there. Okay, just this implementation wise it's looks messy actually. So this A dash you take, right, apply as one of the input to the AND gate, and this E dash also you take, so this have to come here and apply as input to the AND gate. And now for the second one, it is A B dash, and already this A is available here, and I am taking that A like this, and this B dash I am taking, and that I will be applying as input to the second AND gate, right? This is the first AND gate, this is the second AND gate, like that. Now you can observe here that this A B dash also, I mean this 1 and this 0 together, A and B dash, like that they are taking, and this is 1 for this particular input case, this will be 1 and all others will be 0, that you can verify. So whenever this is giving a value of 1, all others will be 0, right? So like this you will get, okay, I am not marking it. So that is the way this AND gate inputs are chosen. And now for you to remember, let me tell you, like for all 0 it is like the first one and last one complemented, and for all 1 it is first one and last one taken as it is. 1 second. Yes, okay. So for all 1 it is taken like a first one and last one, that is AE, okay. Now you can remember these two things. Now for the others you can see some subsequent nearby 1 0 combination they are taking, like this 1 0, so they are taking like A B dash, and here they are taking like this 1 0 is coming like this, right? So B C dash, here they are taking like a C D dash, sorry E dash, like that. Now for here 0 1 like that it is coming, so that they will be taking like A dash B, okay. Here they will take like a B dash C, so here it is taken like a C dash E. Hope you understand the way it's taken, okay. But it's a very special input. I'm not so how people are thinking about it, it's the requirement is like only one of the AND gate should give a value 1, and that time all others, that for that particular output of the Johnson counter, all other AND gates should give a value of 0, then only it will work like the ring counter constant that we studied before. That AND gate requirement is also there, but still it's a very easy implementation, because just 2 input AND gates we are using, and that also just 8 numbers. But in decoder implementation and also for n bit we need a n bit AND gate, that's messy, right? Or log n to the base 2 bit, something like that. So it's a complex design, but it is easy design. So what is the conclusion? If you are using a ring counter, so they sometimes they can ask you differentiate between the ring and Johnson counter. Ultimately both are using for the same purpose, that is for the generation of the timing signal for any given digital circuit. And the difference is like in ring counter, the output of the last D flip flop we are connecting as input to the first one, but in Johnson counter it's just twisted ring counter or twisted tail ring counter, like that many different names are there, or Johnson counter, where the complement of the last output we are applying as the input to the first one. So that ring counter is going through a 4-bit ring counter made out of 4 D flip flop will go through 4 different states. Like hope you remember 1 0 0, then 0 1 0 0, then 0 0 0 1, like that 4 different states you are getting, right? That one, just a one, it's just like in a diagonally that one is moving, that one. But if you are looking at Johnson counter, the counting sequence is different. That sequence you have to understand very clearly how you are getting, because the last one complement you are applying is the input to the first one, so that you are using 4 D flip flop, you have a 4-bit Johnson counter that can give you 8 different state, and for that 8 different state you are decode something like decoding, you are doing applying through 8 different 2 input AND gate in a special manner, so that only 8 different circuits you can activate, right? So you can generate 8 different timing signal using a 4-bit Johnson counter, but using a 4-bit ring counter you can generate only 4 different timing signal. So it's something 2 times capacity than that of the ring counter, right? And it's doing AND gates are used, but that is easy to implement, and just 2 input AND gates is what we need. So a k-bit ring counter circulates so that those 2 points you have to highlight, right? So how that connection is made, you can give it just diagram, and then you have to tell about the number of states counted by using k-bit ring counter, k states only, but using k-bit Johnson counter 2k states are possible, so that 2k different timing signals can be generated like that. Okay, so k-bit ring counter circulates a single bit among the flip-flops to provide some k distinguishable states, right? K states, where the number of states can be doubled if the shift register is connected in as a Swiss tail. The tail of the last one is being connected like that. Swiss tail ring counter. A Swiss tail ring counter is a circular shift register with the complemented output of the last flip flop connected to the first flip flop. Like that is what we seen. So in this next slide, you can see that. Starting from a cleared state, I started with 100. Anyway, you can start with all zeros also. The 4-bit Swiss tail ring counter go through a sequence of 8 states. That is what we seen now. In general, a k-bit. Okay, so the important point is the next one. A k-bit Swiss tail ring counter can go through 2k different states, okay, just 2 times that of the ring counter. Starting from all 0, it should shift to 1 and its complement in the first one, like that it will proceed. Okay, so this is the counting sequence and the required decoding. So that is a kind of decoding only, but it's not using the standard decoder circuit, which is complex with respect to the size of the AND gate, right? But here it's just 2 input AND gates what we used for decoding the output, so that makes it special. And Johnson counter is a k-bit Swiss tail ring counter with 2k decoding gates to provide output of for 2k timing signals. So now everything is double, right? 2k different timing signals you can generate. Now decoding of a k-bit Johnson counter to obtain 2k timing signal follows a regular pattern like what we observed already. So the all 0 corresponds to taking complement of the 2 extreme flip flop. Hope you remember, all 0 corresponds to taking complement of the extreme input, that is A complement and E complement. And all 1 is decoded by taking the normal output of the 2 extreme flip flop. 2 extreme flip flop, all 1 normal output you are taking, that is A and E, right? Now for others, all other states are decoded from using adjacent 1001 pattern. Like here it is 10, so that it will be like AB dash. Here it is BC dash. Hope you remember. Here it is A dash B. Here it is B dash C. Like that we are taking. For example, sequence of 7. Okay, so that example you can just see. Johnson counter can be constructed for any number of timing sequence. The number of flip flop needed is half that of the timing signals required. Where in ring counter that many flip flops are needed. So number of decoding gates is equal to number of timing signals, and only 2 input AND gates are needed. So this is what makes this important. So this understanding is very important for you. Yeah, that's all. So again, I'm repeating that ring counter and Johnson counter are very important topic from 5th module. It's specially mentioned in the syllabus. And if you look at any previous question paper in 2015 scheme, you will see this. So give it proper attention, okay, and draw the diagram clearly. Give the timing signal. Whatever things are asked in the question, accordingly you answer. If they are asking you to differentiate, accordingly in a point by point manner you answer. Okay, so don't. Not only for this topic, everywhere if they are asking some differentiate something, some kind of descriptive questions, so always better you have to highlight the points. Otherwise, if you simply keep writing on, you may written all the points, right, but the examiner may not value it, so they may get confused. So always give a very clear way of answering, right? Yeah, thanks for watching.